Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the content of the universe, what has happened since, the history of the universe, the ingredients of the universe, basically a lot of cool stuff happening inside the universe. I love being a scientist and I love chatting to people about all of the cool things I get paid to work on and things that I don't get paid to work on that I also like chatting about. Hey, David Dunn, great to see you as always. If you're a first time viewer, welcome, great to have you. If you're a regular, welcome back. Always nice to see you all coming back for more cosmology on your Sunday evenings or afternoons or mornings, wherever you are in the world. So, yeah, I'm a cosmologist. I study the universe and I love chatting about all of the cool stuff happening in space, in physics, in science in general. So, this is a place where you can ask all your questions. Hey, Ben, great to see you. Thank you for joining, as always. So, this is a place where you can ask any and all questions about whatever you want. Basically, this is an Ask Me Anything. We can cover things like cosmology, science, academic conferences, academia, if you want me to rant, pretty much anything you want. I don't promise to have all the answers. I would be very surprised if I do have all the answers, but I will do my best to answer the questions that you do have. So this works with you all asking questions. If you don't ask questions, then I get to take the conversation wherever I want, and then we get fun topics or me going on tangents. The video is indeed mirrored because then it's much easier for me if I have to point at something. I can unmirror the video, but then it just looks weird. I think we're also used to having our video mirrored in most like Zoom calls and whatever. That it's weird if it's not mirrored. So yes, the video is mirrored, so you'll see that backwards. But I think if I write something, you should see it the right way around. I believe you should be able to read it properly. Hey, David Howden, great to see you as well. The traveling did indeed go well. So there wasn't a Cup of Cosmology last weekend because I was traveling. This past week, I have been at a conference in Stavanger in Norway, and it was a conference about the LISA spacecraft that is going to launch at some point in the next 10 to 15 years, and that is going to, or aiming to measure gravitational waves in the universe. This is an amazing mission. I am so excited to be involved in this. And we had a workshop where people working on cosmology with LISA got together in Norway and discussed for a week about what we hope to do, the progress we're making, how we're preparing for LISA. It was really, really fun. I learned a lot. I got to speak to a lot of experts, got to meet a lot of really cool people, and I'm more hyped than ever about gravitational waves and the future of gravitational wave astronomy. I think there are good things coming. It's going to be a fun time. There are good things are happening. So yeah. I was away this week. Hey, Ange, great to see you as always. Thank you for joining. Always nice to see you here. Yeah, so it was a really fun conference, and it was in Norway, and I did most of the traveling by trains and boats without using planes because with the climate crisis, we are trying to reduce flying. So that meant the 50-hour journey to get to the conference, which involved multiple trains, a boat, an extra night in Oslo because my night train got cancelled. It was a really fun adventure. And it was exhausting, but really, really fun. And then for the way back, I caught one train and one plane. And I've only caught one plane in the whole journey, and it was the most stressful part of the journey because there were delays, not delays, there was just issues at the airport and a few things like that. And it just reminded me that the train journeys were so much nicer than the plane journeys. So I am trying to do as many conferences as I can entirely by train and boat because it's just nicer all around and it's fun, and then you get amazing views. I took about 400 photos from the train of the amazing views that I've had the last few days. Did a lot of physics as well, but had amazing views. Went on a tangent there, but do feel free to ask me anything you want about the conference as well, or what happened there, what type of stuff we discussed. I can't disclose everything that was discussed, but I'm happy to answer questions about that as well. And yeah, if you're new here, please, or even if you're not new here, please do the usual YouTube things like leave a comment, subscribe, ring the notification bell, all of the usual blah, blah, blah YouTube stuff, like and subscribe, you know how it works. That really does help boost engagement, and I do appreciate all of you who do that. It does. Every little bit helps. We are a couple of cosmology moved around a bit. I was on Periscope at some point, then I was on Haps. I've been on YouTube now for exactly 18 months, And by the end of today, I expect to reach 8,500 views across all my videos, depending on how many of you turn up today. So thank you for that. That's really cool. 18 months, 8,500 videos. I'm very happy about that. So thank you everyone for coming here and tuning in every week. So yeah, this is an Ask Me Anything. You can ask me anything you want and I will do my best to answer. We already have one question here that I'm going to jump into, but as always, keep your questions coming and I will do my best to answer all the questions by the end of the stream. Okay, if you were live streaming video, question from Ben, if you were live streaming video to Earth from a spaceship traveling at 50% of the speed of light away from Earth, would your video be sped up, slowed down, or normal, and why? So that is a good question. And if we're talking about, so let's think about this. The question here is, how are we sending back the information, right? And let's say we're sending it back as a package deal. So one thing that we do have to consider is that there is going to be the delay because of the spaceship moving further and further away, that when you send the signal, it's going to take a while to get there and come back. As to the transmission itself, I think it would be normal speed. The reason for this is that light always travels at the speed of light. So if you convert the video into an electromagnetic signal and send that, or into a radio wave and send that, which is also an electromagnetic signal, then that package itself, that information, is not going to be sped up or slowed down because light always travels at the speed of light. Regardless of how fast I am moving, if I shine a torch, the light from that torch is still going to travel away from me at the same speed of light. Even if I'm traveling at 99% the speed of light, that light is still going to travel away from me at the same speed of light. So assuming we package up the video that I'm streaming and we send it as an electromagnetic wave, then this is not going to be affected regardless of my speed, because that is going to propagate at the speed of light in a vacuum. Of course, then it's going to have its usual interferences and blah, blah, blah. But there will be a delay in the information reaching you, because as I'm moving away, it's going to take longer and longer and longer for the information to reach you. Won't the radio waves carrying your transmission get redshifted outside the range of detection? At some point they will, yes indeed. So this is the thing, as I'm moving away, the light is going to be redshifted. So it is going to gradually move away and away, and then it becomes harder to hear. But it is an interesting question, and I would have to calculate exactly what happens. But also, we don't really have the technology to travel at 50% the speed of light and to do a live stream while traveling away. Usually when we send spacecrafts and so on to space and telescopes, they send information back in packages, and you tune in for a while, you get all the package of information. It's not a continuous transmission, because then continuous transmissions, you do have the problem of things being redshifted due to the motion of things moving away from you. So while it would still travel at the same speed of light, the frequency would be distorted because of the redshifting due to you traveling away. So currently, it would be really cool to do a live stream from space. I'm not sure how we would even go about doing that technologically wise, but it would be really cool. Like we have done live streams from the International Space Station by now, not me personally, but there have been live streams from the International Space Station. So it would be really cool to do one of like something further out there. Obviously, we've had some streams and video feeds, at least, of some spacecrafts being launched and so on. But yeah, reaches a point where it becomes quite hard to get the signal back. But it's very cool to think about. And I'm going to use that to segue into the fact that light travels always at the speed of light is extremely useful. Would time dilation inside the ship take effect? So, me personally traveling on this ship, traveling at 50% the speed of light, I will not notice any time delay effects, because the time delay is with respect to an outside observer. So let's say I'm on a spaceship traveling away 50% the speed of light. As I'm doing that, for me, nothing is changing. I am still just traveling as I'm going. However, for you down on Earth, if you looked at my clocks, you would see my clocks or things on my spacecraft moving slower because of the time delay effect. So even though for me traveling on the ship, I wouldn't notice any difference, those of you down on Earth would see a difference on how time is passing for me with respect to how time is passing for you. An example, if you are to go down to a black hole or a planet with a huge gravitational pull, let's not put black holes in here. Let's say you go down to a planet with a huge gravitational pull, you're going to experience time differently to somebody caught up in the spaceship. This is one of the good things from Interstellar, that they actually portray the movie Interstellar actually portrayed time dilation effects quite accurately. So there is this time delay effect, but the person, you never realize that your time is delayed or slowed or like sped up or slowed down. You will always experience time as passing at 1 second per second. It's just when other people try to measure how time is passing for you that there will be this difference. And then if people come back and compare, this is where things get funky, because then you have different amount of time passing for different people. And as David Dunn is saying, this live stream of spacecrafts was recently done for the Mars Express when they showed Mars live, of course, with the time delay of how long it takes a signal to actually reach us, which is not such a big delay. I think it's 8 minutes, 5 minutes to Mars, something like that. No, it's 8 minutes to the sun. Yeah, it's order minute, so there is a time delay between, stuff happening at Mars and us seeing it, so it is live with a delay. But it is still, they did still do this with Mars Express. There was this live stream. And it's very cool to get more and more videos and images of stuff coming from space. It's also slightly gimmicky, because while this live stream, 16 minutes to Mars, thank you, David Dunn, currently, based on the current position of Mars on Earth, there is a 16-minute delay. And adding on this camera capability that can send back live images is really cool. It gets a lot of attention, but it doesn't really advance the science goals of the mission much. It's just something that is cool and gimmicky, and then we get to watch it, and it generates more interest. So it's always good that people do that. But also, it's not completely necessary in terms of the science that missions are doing. But it's always very nice to see more cool space stuff happening. But the fact that the speed of light is always constant, even in a vacuum, regardless of whatever speed you're traveling at, means that light can be used as a very, very, very precise ruler. Because imagine you want to measure a distance, but then this distance changes because of something like a gravitational wave. Then at that point, it becomes quite hard to measure things because your ruler also changes. But you can use light to measure distances, because you know that light is always, always, always going to travel at the speed of light. So based on how long it takes light to travel a distance, you know how the distance that it traveled, because you know the speed at which it's traveling, regardless of anything else happening. And this is how we measure gravitational waves. Same as the maximum time Deanna can go without mentioning the CMB. You are right. I cannot go more than 5 minutes without mentioning the CMB. We are 12 and a half minutes into the stream and the CMB has not yet featured. This is completely unacceptable, as you say. And just to make sure that you are correct, that I don't go 16 minutes without mentioning the CMB, at the 13-minute mark, you get the cosmic microwave background radiation just because you requested it in there. Never going to pass up a chance to flash that image at people. I'm really feeling the effects of the conference, the lack of sleep, the walking this week. Like, my whole body is just aching. It's been such an exhausting week. And now I just moved and everything's like, I need to sleep. Anyway, don't mind me. I'm just recovering from conference. Do we know the speed of light in a vacuum from measuring it in a perfect vacuum? We know it from calculating it. You can use Maxwell's equations and so on, and from empirical evidence. You can create an almost perfect vacuum and put light through there, and you can measure it. So we have reasons to know the speed of light. We have measured it empirically in a lot of different cases. We know how fast it should travel in a vacuum. You can also shine light through a lot of different things and see how it travels, and then you get the difference in different mediums. We know how fast light travels in water. We know how fast it travels in air. We know how fast it travels in a vacuum. And to be honest, the difference in these three mediums is really, really, really small. Even when light is traveling through air, it doesn't slow down so much because air is a lot of empty space. So we can actually measure the speed of light in near perfect vacuums and a lot of different things. Creating vacuums isn't actually too hard. You just suck everything out and you have a vacuum. So we can measure the speed of light in vacuums and in different experiments as well. So we're pretty sure about the speed of light. It's something that we're quite happy about, our measurement of the speed of light. If space-time can expand faster than light speed, what would happen to a beam of light while that was happening? Would it get carried along at faster speed or get left behind? This is an excellent question and a fun one to think about. So I've thrown out gravitational waves twice now. People aren't asking, so I'm going to come back to gravitational waves at some point. So we know that space-time is expanding. The universe is expanding. Everything is moving away from everything else. And this is happening a lot faster than it did in the past. So the universe is undergoing what we call accelerated expansion. Things are moving away from us, and they are moving away from us faster than they have at any other point recently. The reason this is happening is because of dark energy. We think dark energy is this weird type of energy that accounts for 70% of the energy budget of the observable universe. It is responsible for pushing everything outwards, and that's pretty much everything we know about dark energy. It is driving the accelerated expansion of space-time. But the current expansion of space-time, accelerated expansion, is not the only one we've had. We believe that when the universe was very, 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 very young, in its infancy, it experienced the period of inflation. So if you look at the sketch of the history of the universe, you can see what today is on the right-hand side, kind of over here, and early universe is over that way to the left of the plot. Today, 13.82 billion years after the end of inflation. And if we go back, you can see that at some point the universe was very, very, very small, very dense, very hot. And this expanded and inflated into the universe that we know of today. In order to explain a lot of things in the universe, like for an example, why this map looks so similar in every possible direction you look, one of the ways or the best explanation we have for this is that at some point everything was very tightly packed together. The universe was very, very, very small, and then experienced a phase of inflation, which was exponential expansion. During this period of inflation, space-time itself expanded faster than the speed of light in a vacuum. And this might sound weird because we always say nothing, absolutely nothing can travel in the universe faster than light in a vacuum. However, there is no such restriction for space-time itself. So nothing can move through space-time faster than light in a vacuum, but space-time itself can expand at any speed it wants to. So during inflation, there could have been a period, or there was a period where the expansion was faster than the speed of light in a vacuum. Of course, it's quite difficult to talk about what we mean by faster here, because, and that's why I keep putting the bunny rabbit ears on things, quotation marks, bunny rabbit ears, same thing. Because when we're talking about velocities and speeds, it's always with respect to somebody. You know, if I shine a light beam, I'm measuring that light beam traveling a specific direction and distance. You can calculate its speed with respect to other things in the universe. But calculating the speed of expansion of space-time, what observer do you take? Where do you position yourself in order to measure this or to relate it to something? So it becomes quite difficult to talk about the speed of expansion. So when we say the universe expanded faster than the speed of light, it's like, yes, technically it did, but also, is it really fair to say that the universe expanded faster than the speed of light? But all of that aside, that's not the question, that's just background information to the question. The question, if space-time can expand faster than light speed, what would happen to a beam of light? Beam of light will still travel at the same speed of light. It doesn't matter if space-time is expanding or contracting or whatever space-time is doing. Lights will always, always, always travel at the speed of light in the vacuum, to the best of our knowledge. This means that light would no longer be able to travel far. Basically, if space-time is expanding faster than light can catch up with it, you would stop seeing light. And this is something that may potentially happen in the future again. We know that the universe is undergoing accelerated expansion. If this expansion speeds up and it starts expanding at a greater rate and a greater rate and a greater rate, at some point, all of the galaxies that can send us light will be so far away in the night sky and being pushed away that their light will never reach us. It could be that the universe expands so much and so dramatically that it keeps increasing and increasing and increasing, that in a billion years, everybody in the universe would think they're completely alone because they would not see any other stars or galaxies or any dots in the night sky. So billions and billions of years into the future, if dark energy carries on increasing, we might reach a point where you look out and nothing's looking back. So it's actually really cool that we exist at this specific time in the history of the universe when we can still look out and see night sky. We know the universe is expanding. We know this expansion is accelerating, but we can still get information from the night sky. Someday this might no longer be the case. This is one possible scenario. This would eventually result in what we call the heat death, the death of heat. Hey, Scott, great to see you. No worries for being late. I'm not taking attendance like you came in late. Come in when you feel like, come and go as you please, and you can always watch the replay if you want to catch up to what you missed. So, yeah, if this accelerated expansion continues and things get further and further and further away from us, we would end up with the heat death, the death of heat. Very dramatic. This is also known as the Big Freeze, where everything would be so far away from everything else that you would have no interactions, no exchange of information. You'd basically be you'd be in a cold, empty, dead, desolate universe by yourself without being able to contact anyone anywhere outside in the universe. Heat death, fun scenario. Another possibility is that the accelerated expansion speeds up so much that it becomes strong enough to rip everything apart at the seams, and then atoms would be torn apart and the whole universe would be completely flung apart. This is what we call the big rip, like ripped in half. It would be ripped apart at its seams. Also a fun scenario. So the end of the universe is quite dramatic when we think about it, but light will always, always, always travel at the speed of light. And if the universe expands too quickly, light will never be able to travel around. All the stars will go dark, and there won't be a TARDIS exploding to set it right. So, and I hope people get that reference. So yeah, light will always travel at the speed of light, regardless of the expansion rate of the universe. This could result one day in the future, depending on how dark energy behaves, this could result in a heat death where everything is so far away that it cannot exchange information in any meaningful way. We could also end up with a big rip where the universe is torn apart at its seams. Or we could end up with something even more dramatic, like the expanding bubble of death if you have a random vacuum decay, and then you just completely delete the entire universe and reset it. That's also something that could literally happen at any point. It might even have happened. There might be this expanding bubble of death heading towards us, and there is literally nothing we can do. We would not see it coming. We would not know what hit us. We would literally just stop existing, us and everything, the whole universe. Which is fun. It's cool to think about all the ways the universe might end. So, some people find this a bit scary, and I get why. Because all of these things are very far into the future, except the bubble, which could happen at any point, but we don't think it's likely. But the fact that the universe is not going to be around forever means that, we are privileged to be here in a point where we can see stuff in the night sky, where we can get information, where we still have access to the CMB. That's another thing. As light continues to get redshifted in the universe, someday people are going to look up and they're not going to see this. The CMB is going to be redshifted beyond recognition, and people will not be able to see it, which means the information it contains will be lost. So at some point, there will be maybe some species who will have an empty night sky and won't even have the CMB. So it's amazing that we're alive in a time where we can look back into the past of the universe, where we can look into the night sky and see things. It's very, very cool. So I hope the eventual death of the universe doesn't upset you or depress you too much, because it's a really fun topic to think about. And it's always cool. You meet astrophysicists or cosmologists and you ask, how is the universe going to end? And we get ridiculously excited about this. Like, we should not be so happy about how the universe might end. So yeah, light always, always, always travels at sea. That is the conclusion to the question asked there. Because of this, we can use light to measure gravitational waves. So what are gravitational waves? Gravitational waves are ripples in the fabric of space-time itself. If a gravitational wave travels through you, you will first get thinner and taller, and then shorter and fatter. But this difference is going to be tiny. Imagine you have two black holes that smash together in a cosmic dance. They start a cosmic dance, they spiral around, they smash together. They produce a huge amount of gravitational waves. They might release like 3 or 4 times the mass of the sun in the form of energy and gravitational waves. But by the time this gravitational wave reaches us, if a gravitational wave hits me, I would only grow by 1/1000th the width of a human hair. It's a ridiculously small difference. So how do you measure such tiny, 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 tiny differences in distance? Well, you use lasers, because lasers are light and therefore will always travel at the speed of light. Gravitational waves are an amazing thing. They were predicted by Einstein's general relativity over 100 years ago. We say Einstein's general relativity. General relativity was developed by Einstein and many others who went uncredited, including Einstein's wife. But in general relativity, we predict gravitational waves. And these gravitational waves are tiny. And Einstein himself said we'll never have the technology to measure this. But we did. In 2015, we got the first direct detection of gravitational waves, which is amazing. We built two experiments, LIGO Livingston and LIGO Hanford, where we have an L-shaped detector. Down here, you send the laser back and forth across both arms hundreds of times. comes back, you put the light together. If either of the arms change distance, even by the slightest amount, when the light comes back, you'll get a pattern. Based on that pattern, you can say a gravitational wave came through. We've done this hundreds of times by now, thanks to LIGO, the two detectors in the US, LIGO Hanford and LIGO Livingston. Now there's a third one in Italy as well, Virgo. Cagua is also in the game. And with all of these, you can actually measure gravitational waves to the point that you can pinpoint, like several billion years ago, in that point in the sky, two black holes smashed together and produced gravitational waves. And this is something we have been able to measure, and it's amazing that we've been able to measure this. LIGO has done 3 operation runs, and they have measured over 100 events of these, of either black holes smashing together, neutron stars smashing together, or black hole neutron stars smashing together. And it's really, really cool. And LIGO just turned on very recently for run 4. So, this is something that was an incredible achievement. The first gravitational wave announcements, we were ecstatic. Scientists everywhere were like jumping up and down. I did a live stream right after they announced it. Anyone who remembers that knows how hyperactive I was there, even more than usual. It was amazing. And now it's become so commonplace that you can literally get Twitter notifications. There's an app you can download. It sends you a notification every time something goes off in the LIGO detectors. It's amazing. It's so commonplace now that there's literally an app sending you push notifications like, hey, we got a signal. Hey, we got another one. It's really, really cool. LIGO alerts on your phone. So, yeah, gravitational waves are a thing. We know how to measure them. It is really, really cool. But so far, we've already measured ones coming from black holes smashing together. But there are so many other things out there that can produce gravitational waves. For an example, a small black hole falling into a big black hole would produce gravitational waves. Or neutron stars spinning around produce gravitational waves. Or even the universe itself could produce gravitational waves. We mentioned before about this time of inflation, this exponential expansion in the early universe. If there was a period of exponential expansion, this would have been so dramatic that it could have left gravitational waves in the ripples of space-time itself. In the same way, we have the cosmic microwave background radiation, so this amazing image of the afterglow of the Big Bang itself. This is all with light. But there could even be something similar made of gravitational waves. We could have a background of gravitational waves everywhere in the universe. And these are they're too small to be measured by LIGO, by ground-based detectors. So to measure these, we need to go somewhere quieter that has no interference, that is harder to get to, harder to do everything, but easier to deal with in terms of pushing our sensitivity, pushing how much we can measure. We've detected neutron stars crashing into each other with LIGO and Virgo, which is amazing, because when two neutron stars smash into each other, they produce gravitational waves, but they also produce electromagnetic waves. They also produce a huge burst of light. And this is one of the reasons that LIGO sends out these live announcements. It's not just like, oh, it's fun, you get a push notification for a gravitational wave. It's because if you have a gravitational wave that comes from two neutron stars smashing together, you're also likely to get the electromagnetic radiation as well. So then if you work with a big telescope, for an example, or you have your backyard telescope, you can get the push notification telling you, like, look, approximately this patch of the sky, and then you turn your telescopes there. Obviously, an amateur telescope may or may not do well here. But this is exactly what they did a couple of years ago with the first neutron stars that smashed together that we found in LIGO. And Virgo, the announcement went out to everyone working on big telescopes, like, hey, look up there. And then we measured the same event of two neutron stars smashing together with gamma rays, with X-rays, with normal light. You measured the whole spectrum of it. So for the first time, we were actually able to do multi-messenger astronomy, which means getting the same information through different sources. We got gravitational waves, we got electromagnetic waves that allowed us to learn so much about neutron stars, about where gold comes from, about where a lot of stuff comes from, about the expansion rate of the universe, about how fast gravitational waves travel. They travel at the speed of light. It's amazing that we can do this. And as David is saying here in the comments, David Dunn here, the gamma rays and the gravitational waves arrived within 2 seconds of each other from 200 million light years away. This is incredible. Einstein's or general relativity predicts that gravitational waves travel at the speed of light, but a lot of theories beyond general relativity don't. So when we got this measurement, kind of confirmed that gravitational waves do in fact travel at almost the speed of light, or as close as you can get given the uncertainty in the detectors, which is really cool because it's a prediction of general relativity that we measured. So that's really, really cool. Would wormholes emit gravitational waves? That is an excellent question. Wormholes. Do wormholes emit gravitational waves? Or we just got random pop-ups popping up on the screen? Okay. So a wormhole is a hypothetical thing that may or may not exist. And what a wormhole would be is basically a tunnel through space-time. So we always think of space-time as being flat. What a wormhole is a bridge between 2 points of space-time. However, this bridge is hypothetical. Wormholes are hypothetical. So would a wormhole produce gravitational waves? I'm going to say no, because you can think that wormholes are a solution to the equations of general relativity, in the same way that black holes are. Black holes are something that mathematically you can pull out of general relativity. The same is true for wormholes. You can pull them out of general relativity. We've never observed them, but they are something that exist within the framework of general relativity. And much like black holes, they are kind of stationary objects. Black holes emit gravitational waves when they spin around another black hole, or when they crash into each other, or when there's something happening. But an isolated black hole just sat there doesn't produce gravitational waves, because you need acceleration. You need some type of movement. So if you have a wormhole, if it's a stable wormhole, it should not have any acceleration, I think. I might be wrong about this. And if it doesn't have any acceleration to it, it will also not produce gravitational waves. Then you can do fun games of what if a black hole falls into a wormhole? Does this produce gravitational waves? And I would say probably yes. But because we don't have any actual evidence for wormholes, other than they're fun to think about, it's quite hard to think about this. I'm sure we could mathematically pull this out, but I'm going to say that wormholes by themselves do not produce gravitational waves. However, if you were to hypothetically have a wormhole doing something with something else, then you might get gravitational waves. Gravitational waves are easy to produce. If I start spinning and moving my arms, I'm going to produce gravitational waves because I have non-symmetrical acceleration. If I just spin like this, I'm not going to produce gravitational waves because the motion is symmetrical. It's like if you spin a football on your finger, you don't produce British, normal actual round football, a ball. You're not going to produce gravitational waves. If you spin a wobbly rugby ball or an American football on your finger, you will produce gravitational waves because you have the wobble to it. So to produce gravitational waves, you need two things. You need acceleration and you need lack of symmetry. I don't think wormholes fulfill either of those two criteria, so I'm going to say that wormholes do not produce gravitational waves. However, this is very hypothetical, so I'm not sure about this answer. Question from Smithy of, do we know why they didn't get here at the same time, talking about the gamma rays and the gravitational waves? These traveled for 200 million light years, so 200 million light years away. This is a ridiculous distance. The fact that they came together, I can see you, James. Hopefully you can hear me as well. I do read your comments, James. So 200 million light years is a huge distance. The fact that these things came together or arrived here within 2 seconds of each other is amazing. It's such a tiny, tiny, tiny difference that it's less than... So I think it was like the 6th or 7th digit. So we were able to say that they traveled at the same speed to within 0.0000001% accuracy. So the fact that they came 2 seconds apart is a negligible difference given the distance they traveled. There are some explanations about the way the gravitational waves are produced as things are coming closer together, while the gamma ray burst is once they've actually collapsed. So there is a slight difference you might expect, but it was within the compatibility range where you say these things came together. They came at the same time. So the tiny difference of 2 seconds across 200 million light years, it's as if I were to shoot a dart from Earth. You put a dartboard on the moon and I shoot here from Earth and I get it just very, very close to the center, but not completely at the center. You're not too bad if I shoot a dart from down here to the moon and just miss by a bit. So the fact that it was less than 2 seconds means it's just a tiny, 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 tiny difference and not meaningful in any way. Hey, Guadav, nice to see you. How are you wonderful people doing today? Thank you for asking. I am doing very well. I am very tired, just got back from a conference, but very energized and both tired but motivated about work and motivated about a lot of things. I am doing well. I hope everyone in the comments, and yourself included, is also doing well. So I do want to come back to the gravitational wave comment, but there was another question by Smith before. If scientists like being wrong, why do they use evidence? Not using evidence would result in you being wrong almost all the time and being in constant state of bliss of wrongness. I mean, we like being wrong, but we also like being right. The way we do science is by getting as much evidence as we can to form consistent theories and models and predictions to be able to understand the world around us. I think a lot of scientists don't agree that we like being wrong. We like our theories and models and stuff to work. We like understanding the world around us. This is the point of science, and for that we have to use evidence, we have to use data, we have to use facts. And if you've been working on a model for 100 years and then some new data comes along and says no, a lot of people are going to be like, oh, okay. But it's always interesting when it happens because it means you get a chance to go and redo your stuff and try again and improve the theory. And it's usually fun if it's not happening to you. If a theory is proved wrong, you're like, oh, wow, now we get to do this again. But if your favorite pet theory is proved wrong, then you're like, okay, kind of wasted my time on that one. So we have to use evidence and facts and data because that is what the scientific method relies on. So we use all of this. We construct our theories, our models, we make predictions about the world. And sometimes we're right, sometimes we're wrong. And that's how science progresses. You do your best guess now, and then you get more information, so you update your guess. And at some point, there's no longer a guess. It's a well thought out explanation. Still catching up from a comment from Scott here. Still catching up, but it still blows my mind that so many elements that we use every day were created by neutron star mergers. Yes, all of the gold that we have, we think was actually created when neutron stars smashed together. That seems like currently, based on what we saw from these two neutron stars smashing together, it seems like gold is actually fused in these massive neutron stars smashing together and then spread out throughout the universe. So any gold particles that we have here on Earth are thanks to neutron stars smashing together, which is kind of cool to think about. There's a question here that I feel like it's the start of a joke and I don't know the punchline. So the question is, I wanted to ask, why did the sun go to school? I feel like there's a punchline coming and I can't figure out what it is. So please do let us know if that was an actual question or if there is a punchline coming there, because I feel like there is going to be one. Just checking that I did not miss any questions before, because I know I skipped through some that I was planning on coming back to. We covered wormholes and gravitational waves. No superheated tea today. Indeed, I actually made my tea 10 minutes earlier than I usually do, so that then I wouldn't have to wait so long to drink my tea. Okay, there is a question about the Higgs field that I want to come back to. The sun went to school to get brighter. Of course it did. That is, I appreciate space jokes. Thank you for that. There's also an element of Schadenfreude and other scientists being proven wrong. In a way, yes. There's also an element of like, oh, wow, why am I not working on that when other people do cool stuff? The problem about being a scientist is there's so many cool things to work on. Okay, back to gravitational waves. I know there's a Higgs question. I'm making a note of Higgs question to come back to later. But I want to talk about something cool about gravitational waves. And I am leading up to something here, but I talked about gravitational waves, black holes smashed together, neutron stars smashed together, ripples in space-time. And there's a question that people on this stream have asked me, on Cup of Cosmology have asked me multiple times, is can you get lensing of gravitational waves? So we know that light that travels through the universe gets lensed. If you have a big, massive gravitational object, light waves will bend around this, they'll be distorted. And this means that by the time the light reaches you, you see a distorted galaxy, or like all of the, if you look at the deep field images from Hubble or the JWST, there's always these kind of distorted galaxies. And this is because of gravitational lensing. And I am actually looking for an image while I'm saying this. This is because of gravitational lensing. So big, massive objects with a lot of gravitational pull will distort light as it travels around it. This creates a gravitational lensing effect. For an example, here is the Hubble Space Telescope deep field image. And here you can see a lot of these like sheared galaxies that look like you're basically holding up a lens to these galaxies and they are slightly distorted. This is because of gravitational lensing. And a question I've been asked often on this show, or at least more than once, is can gravitational waves also experience lensing? If a gravitational wave is emitted by two black holes smashed together, this emits gravitational waves. On their path towards us, these gravitational waves pass through a cloud of dark matter or close to another black hole. Are they going to be lensed? And the answer is yes, they are. So gravitational waves do experience lensing in the same way light does. But it's such a tiny effect on top of a tiny effect that it's really, really, really difficult to even think about how we're ever going to measure this. But there was someone at the conference I was at this week who was talking exactly about this, about how we can hope to do stuff with lensing of gravitational waves. It's like a tiny effect on top of a tiny effect, but it's something that theoretically you can predict. And if we're ever able to measure this, no idea how we would ever measure lensing of gravitational waves, but if we're ever able to measure this, we would learn a lot more about dark matter and about things like that. It's a new way of measuring things like this. And the reason I'm mentioning this now is because I listened to this talk and I was like, oh, wow, this is so cool, you know. And it's not something I'm in any position to work on. I wouldn't have the knowledge for it. But it's one of those things like, I want to work on that. Like, that just seems fun. So it is always a thing. You go to conferences and some of the stuff you're like, I'm glad someone's doing that. I'm glad that someone is not me. But other things you see like, wow, this is so cool. I cannot wait to read the paper and see what you've done. And I was so interested in this talk about lensing of gravitational waves. It's so fun to think about. Tiny effect upon a tiny effect. So yeah, sometimes we do get schadenfreude, this like fear of missing out kind of thing when someone else is proven wrong, but also when someone else is working on a cool topic and you're like, oh, that's so fun. I want to figure out everything about this topic. Tell me more. So yeah, then I went to the person who gave the talk, like, tell me more. And it was really cool to hear about these things. Okay. I am aware there is still the Higgs question. I'm going to come back to the Higgs question. More gravitational wave stuff. I should drink water in addition to drinking tea. I have been told that I drink too much water because on the multiple train journeys that I've done this week, I needed to take with several bottles of water with me. It's like, it's a 7-hour train journey. I'm going to get through over 2 liters of water. Yeah, I was getting through all the water I was taking with me, and apparently I drink a lot of water. I don't think that's unreasonable. So, comment from Scott, I assume they use a sophisticated program to calculate the amount of lensing and recreate the original image. This is what we do with normal images, like with light images. We can account for the shear. You can mathematically calculate how much something has been sheared, and based on that, you can get some ideas. For the gravitational lensing, it's the same. It's like a theoretical calculation of how much something changes on top of something else. If a lecturer made a mathematical error, I would just quietly leave the room. You know, everyone's human. We all make mistakes, and it has happened. I've made mistakes during lectures. I've made mistakes during live streams. And I think, you know, it's a thing that happens, and sometimes people make mistakes, and that's okay. You can't expect your lecturers to know everything. Lecturers do make mistakes, and it's very easy to make mistakes when you're doing a calculation on the board. But yeah, it's we can calculate this lensing of images, and we can calculate the theoretical prediction for how much a gravitational wave could be lensed, which is very, very, very cool. Comment from James, do we determine the source of every gravitational wave detected? Is there a way to determine the magnitude between gravitational waves detected? So the problem with trying to find exactly where a gravitational wave came from is that it's quite hard to triangulate. With the two LIGO detectors, you can get a band. So if an event is detected in both LIGO detectors, you get a band across the sky. You say it's somewhere in this band, in this area, you know, in this region. But in order to get a good idea of to where everything came from, so in order to really determine the source, I realize that this might not be the question you're asking here, but in order to figure out where the event is, what you need is three, at least three, and then you can triangulate. And this is why it's really cool that in addition to the two LIGO detectors, we have Virgo in Italy. So the two LIGO ones are in the US, we have Virgo in Italy, and we have Cagra as well. So yeah, if you only have your gravitational wave in two detectors, it's quite hard to pinpoint. If you get it in three, like the two LIGO and the Virgo ones, or two LIGO and Cagra, you can triangulate it to quite a nice area. Like, it's not just in this band, it's in this blob of the sky. As to what caused the gravitational waves, which I think might actually have been your question, we know that the shape of the gravitational waves is going to be different if it's two neutron stars smashing together, two black holes smashing together, or a neutron star and black hole smashing together. And people have ran billions of computer simulations of what the different wave shapes would look like depending on the origin of the gravitational waves. And then once you have your detection, you compare it to your catalog to see which one it's like. So then you can say that based on the shape, this came from two black holes, or it came from two neutron stars, or a black hole neutron star. Sometimes if the mass is very, very similar, it's not completely clear. And sometimes they're like, well, we think it's this, probably. So we can determine the location if we get three detections, or at least a band if we get two. And we can determine what caused the gravitational wave if we are actually able to measure it properly. Then we compare to the template and we can figure out what caused it. So your question there was, do we determine the source? I think that answers that. Is there a way to determine magnitude between different gravitational waves? So what we measure is the strain, so how much, so the kind of the amplitude of the waves, the frequency, and the overall shape, because the shape will change depending on the origin. And with this catalog of like thousands of simulations, you can always compare to one of these and see which simulation best fits the one that you have. Hope that answers the question. Feel free to ask if it doesn't. My professor made a mistake. I demand a tuition refund. Yeah. I don't think it works like that, unfortunately. There is a saying in English, an apple a day keeps the doctor away. 3 litres of water a day keep kidney stones away. Exactly. It's healthy to drink 3 litres of water a day, and I will accept no criticism about my drinking habits. My water drinking habits. God, that sounded bad. And as Scott is saying here, in order to measure more gravitational waves, and going back to what I was saying before, what we do need is a bigger detector that goes to somewhere quieter. So I'm going to show you the different types of gravitational waves we can have. So here there's a lot of stuff happening. In the center, you can see this kind of spectrum that's similar to the electromagnetic spectrum, red on one side, purple on the other. You have origins of gravitational wave at the top, sources. You see this red arrow that says quantum fluctuations. These are like the things the universe creates. You have supermassive black holes smashing together. You have compact binaries. This is like white dwarfs. You have rotating neutron stars, supernova. And at the bottom, you can see the detector, and there's one circled here. And this is LISA, the Laser Interferometer Space Antenna. It's an acronym. Depending on who you ask, it's pronounced either LISA or LISA. So LISA is a gravitational wave detector that we plan on sending to space. And instead of just being 1L, we're basically building 6 of these. So you need 3 detectors. You put them in a triangle. You bounce lasers between each one. So then you get 1L there, 1L there, 1L there, sorry, 3 Ls. So then you get all of these in both directions. So 3 detectors, you send them to space. You keep them in a perfect triangle. These 3 detectors are going to be chasing the Earth as it moves around the sun. So you have sun, you have Earth moving around the sun. And the 3 LISA detectors will be chasing the Earth, sending lasers back and forth. These 3 detectors will be separated, so the arm length is going to be 2.5 million kilometers. For comparison, the LIGO ones we have here on Earth are 4 kilometers, which is massive for here on Earth. In space, they're going to be 2.5 million kilometers apart. They're going to send lasers back and forth, and they're going to look for any ripple in the fabric of space-time. It's amazing. This is an incredible feat of ingenuity. The fact that we've come up with this experiment, the fact that it is mostly funded, it's going to launch. We expect it to launch within the next 10 to 15 years. What is LISA going to do for us? LISA is going to measure black holes smashing together. It's going to measure galactic binaries, so white dwarfs so pairs of white dwarfs within the Milky Way. It might measure black holes falling into massive black holes. It might measure supermassive black holes smashing together. And my personal favorite, and the reason I care about LISA, other than its call, it might measure the ripples of space-time itself. The ones created in the early universe, so that someday, in addition to having this amazing map of the light of the early universe, imagine if we could have this of gravitational waves as well. Like, not only light, but here's the gravitational waves of the early universe. That would be amazing. And unfortunately, this is ridiculously complicated, and we don't expect to get this level of precision with gravitational waves. Why not? Because there's a lot of stuff to take care of. Unfortunately, the lasers do not make a pew pew pretty laser noise because there's no sound in space, and also you don't actually see the lasers. They're kind of not visible light lasers. LISA is set to launch at the end of 2030, so 2036, 2037, depending on who you ask. So it's about 15 years away. But it's technologically extremely difficult because here on Earth, you build the detectors, they're staying there. You know where you put it. But when you launch something to space, it's going to be moving around a bit. So each of these detectors has what we call a test mass inside. And this test mass is what follows general relativity, and you can calculate the position. But there are going to be issues like the spacecraft might move very slightly, 2.5 million kilometers distance. They might shift by a meter or two. So sometimes the lasers are going to come back already out of sync because of the movement of the spacecraft. So we need to take into account the movement of the spacecrafts. We need to take into account the spacecrafts themselves that are generating heat to actually function. You need to take into account so many things that there's going to be a lot of instrument noise and mission noise that we need to be aware of and we need to take care of. Then you have all of the other things that LISA is going to measure. So for me, I want this signal that is behind everything else, like the background. So imagine you go to a rock concert and you want to listen to somebody whisper the other side of the room. And you have the megaphones going off, you have the speakers going off, you have people chanting, people singing, you have people screaming behind you, and you're trying to listen to that whisper. You need to get rid of everything else. The concert venue, you have the aircon making noise as well. You need to get rid of everything. And that is what I'm trying to do. And not just me, that is what people at LISA Cosmology are trying to do. So this last week in Stavanger, we've been talking about this, approaching it from different angles. Everyone has their own approach, their own differences, their own projects. And it's been so cool because I've talked to people working on the noise part, on how we account for the instrument itself. I've heard from people working on the different things that LISA is going to detect, people working on similar to what I'm working on, people looking for primordial black holes with LISA. There's been so many potential ideas this week of I want to do this, I want to do this, I want to do this. And the point of this conference is to put all of our thoughts together so that we all know what everyone else is doing. On the last day, we had a recap of this is what we want to do next. And it's really nice to have so many people come together as a big collaboration and say, like, this is what we're going to do with LISA once we get data. Give us data. This is the cosmology we're going to deliver. And it's been amazing. It's been a really fun week, and I am extremely optimistic about the future of LISA and about the amazing things the spacecraft is going to do. And despite the challenges of the noises and everything, I hope that someday we will actually get this background gravitational wave signal. It will be so fun. So it's amazing. We've built gravitational wave detectors here on Earth, and we're like, that's not enough. Let's send this guy up to space. And now we're sending a gravitational wave detector to space. I'm so excited about this. I love gravitational waves, as people know. Being able to spend a whole week just brainstorming what we're going to do with gravitational waves in the future is amazing and exhausting. There were days where we had like 20 talks a day and then discussion sessions. Completely exhausting. And I managed to go on to a couple of hikes and went out on a boat trip in the fjord. So it was a very fun week. But I am so tired now. So, conclusion, gravitational waves are amazing, ripples in the fabric of space-time itself, and we are trying to measure them. And I'm optimistic that soonish, we are going to send some experiments to space to look for these tiny, tiny ripples using space lasers. Does not get cooler than that. It sounds like the plot of a sci-fi film, like, I'm going to shoot space lasers, I'm going to look for ripples, I'm going to reverse polarity. It sounds sci-fi, but this is what I get to work on, and I get paid to do this. It's amazing. Okay, there was a question I ignored about Higgs. I want to go back to Higgs, and then we can carry on with gravitational waves. There was a question of how well do we understand the Higgs field? Okay, Higgs, the Higgs field is a field, as the name implies. It doesn't help much. A field is something that we use a lot in physics that basically means it has a value everywhere at every point. Like if I ask you, what is this? If I drop my pen, right, I'm going to drop the pen, and I ask you how fast that went, there is one answer. You have the speed of the pen falling down. If I ask what is the temperature in this room, we give the average value. But every point in this room might have a different temperature. So here we can say this is like a field. Every point here has a different temperature. Every point has a value, and we give the overall average. So the Higgs field is something that is everywhere in space-time. And at any point, you can measure the Higgs field, and then we deal with the overall behavior of the Higgs field. Every particle has a field associated to it. The Higgs field is the one associated to the Higgs boson. What is the Higgs boson? The Higgs boson is the particle that gives everything else mass. So in the early universe, things did not have mass. But then the Higgs field turned on, and this gives everything mass. You can imagine the Higgs field is kind of like a thick treacle to particles, like a thick maple syrup. So the particles, instead of moving freely, suddenly you're like, ooh, I'm slowed down by this Higgs field, this treacle maple syrup Higgs field. So the Higgs field is basically this thing everywhere that causes everything to gain mass. Suddenly, like, oh, moving is harder because I'm suddenly massive. Also, if I was in a field of maple syrup, I would just be like, maple syrup. Anyway, particles in the universe get the Higgs field. They absorb it. They get mass because of the Higgs field. So how well do we understand the Higgs field? Pretty well, actually. It's something that was predicted. It was a missing piece of the standard model of particle physics. Like, how do we give things mass? There was a prediction for the Higgs boson. We turned on the Large Hadron Collider in Switzerland, which smashes particles together. It's 27 kilometers of tunnel underground, smashes particles together. Stuff comes out. And we found the Higgs boson multiple times. We found many Higgs. Producing Higgs is easy business for the Large Hadron Collider by now. And the mass gives us a lot of information. So we have a pretty good understanding of the Higgs field, of how it behaves with other particles, of what it does. There are still some open questions, like how do neutrinos get mass? Because neutrinos don't seem to feel the Higgs field, so why do neutrinos have mass? Still working on that one. But we do actually have a pretty good understanding of the Higgs field to some degree. Higgs field gives everything mass. Without this, there would be no mass. And that's why people call it the God particle, because you need God for there to be mass. Anyway, Higgs field gives everything mass. Please don't call it the God particle. It's a very stupid name for a particle. It has much better names, and we're terrible at naming things anyway. So we have a pretty good understanding of the Higgs field. I'm just glad they kept the Simpsons naming convention going after the big-ass radio telescope. Yeah, they should absolutely do that as well. LISA is not named after Lisa Simpson. It is an acronym for the Laser Interferometry Space Antenna, and they just decided having a name was nice. Headcanon, you can name it after whoever you want. If there's a Lisa you like in particular, Lisa Meitner was a very cool physicist, so you might want to name it after her. But in general, please don't name spacecrafts after people, because that is extremely problematic, as we've seen with the JWST. Just in general, do not name your big, amazing telescopes after known homophobes, or even people who might one day turn out to be assholes. Just don't name things after people. Physicists are not worthy of having things named after us. Do not do it. I don't think many people are worthy of having stuff named after them, actually, to be honest. Just give things logical, easy names, or fun names like Boaty McBoatface. Just don't name things after people, because then people turn out to be problematic, and then you have an issue. Okay, so it's almost an hour. I guided the conversation a bit towards gravitational waves, and thank you for the people who helped me get the conversation to where I wanted to go. Gravitational waves are amazing. It's incredible to think that 7 or 8 years ago, we got the first detection. It was novel, it was amazing, it was incredible. And now it's so commonplace that we get the push notifications and it doesn't even register. It's like, oh, we got a new detection. Well done. There's another one. It's really cool that we've come so far. We've had 3 operating runs of LIGO so far, and we've got over 100 detections, and now they're or up to run 4. We're going to have 2 LIGO experiments. We're going to have Virgo. We're going to have Kagra. These are going to be able to measure so many things. And in just a short amount of time that 04 has been ongoing, there's already been stuff. There's stuff happening. It's really, really cool. And on to a bit of cup of cosmology news. I might be able to get someone from LIGO to come talk on the show. That's ongoing. No promises yet, but maybe that's going to happen. So expect more gravitational waves because it is my favorite topic, second favorite topic after the CMB. I think CMB and gravitational waves are basically top spot for my favorite. I love them both equally. No favorites. We don't do favorites here. We love everything equally, but CMB gravitational waves are definitely up there. Expect a lot more gravitational waves going forward, both on the show and in general, because LIGO, Virgo, Kagra are going to give us a lot. And at some point within the next 15 years, hopefully, LISA is going to go up. But LISA is not the only one. LISA is the European one. There is also an Asian experiment set to do the same. There's going to be a Chinese gravitational wave detector going to space as well. Not sure when that's going to launch, but that is also in the works, also next 10 to 15 years, and they will be very complementary, LISA and this one, so even more gravitational waves. Working on an acronym for Maggie, so far best I have is massive, yes. There's actually acronym generators online, like you can put words and it will give you acronyms a la physicist. It's very fun. I'm not going to answer who. We'll see if I can work things out. You'll see. I do have like a list of 4 or 5 people who I need to email to get them on the show. Expect more guests coming soon. It's been a while since I had a guest on the show. Stuff is happening behind the scenes. Do expect more guests coming soon at some point. There's a triangle forming between Deanna, the CMB, and LIGO, and yes, gravitational wave triangle. The thing is, you can love multiple things at the same time. Embrace polyamory. You don't need to be married to one topic. You can love multiple topics and have fun with all of them. A person's name is an essential part of biological taxonomy. Technically, it's a citation of their species description. Yeah. Well, I think I think we shouldn't name things after people, but I know people do that. What if we detected multiple gravitational waves from the same area but cannot determine the cause? Is this scary? No, this would be fun. This would be really fun. Like if we suddenly got bombarded with gravitational waves, then we're going to be like, where's this all coming from? We by now have an idea of like how much gravitational waves are we getting. And if we suddenly got more, like one point in the sky started emitting a lot of gravitational waves and we couldn't figure out why, then it's going to be like, what is happening? That would be so exciting. I don't think we need to worry about anything scary producing gravitational waves, but it's going to be exciting if we were to do such a thing. Is Kip Thorne still involved in gravitational wave research? I believe he is, but more on the LIGO side, and I don't meet many LIGO people. I just meet LISA people, which is also very cool. But I don't meet many LIGO people. I'm having an hell of a time getting a guest from LIGO. We'll see. No promises yet. No promises. Just putting a hint out here, something I'm trying to get to happen. But we'll see. No promises. But expect lots of gravitational waves going forward. Okay, next week, I will not be on Cup of Cosmology on Sunday. Let me just bring up my calendar and confirm. But I think next week there won't be a Cup of Cosmology on Sunday. Okay, so Sunday 18th, there will not be Cup of Cosmology. The reason for that is I'm hosting a dinner party at my place, which means I get to cook for people, which I love doing. And I have so many probably over-the-top cooking plans. I'm planning so much food. It's going to be so much fun. But Sunday evening is dinner plans, which means Sunday next week there will be no stream. As I said recently, if I can't do Sunday, I will try to do Saturday, which means I will probably be online Saturday next week. Same time as usual, just one day earlier. There's a chance I might not be able to, because if I have too many cooking things to do, I might have to cancel the stream. If I'm like still cooking on Saturday evening, then I might not be able to do the stream, but I should have everything like figured out and organized and scheduled. So it should be fine. I will be doing so much cooking. But technically, there will not be CMB pie. There will be my now apparently famous lemon cake, vegan lemon loaf, which I've made a couple times, and this apparently is the best thing I bake, so that has to appear again. I will be doing a completely vegan dinner next week, which is going to be really, really fun. Okay, so Cup of Cosmology will not be online next Sunday, but I will try to be online Saturday. So that's Saturday 17th at the usual time, which is 7 p.m. if you're in Europe, 1 p.m. if you're on the East Coast in the US, 10 a.m. if you're on the West Coast in the US. As always, there is a time zone converter on cosmology.com. You can figure it out from there. And then I could branch out into cookery live streaming. Absolutely not. When I'm cooking, I'm very chaotic. Last thing I need is people watching me cooking. No. That would disrupt the flow of things. Also, when I cook, I have very loud music on. So, yeah. Well, all of you saying your invitation got lost, you're not in Finland. I can't help if you're not in the right country. But yeah, next week, Cup of Cosmology should be online on Saturday. And then the week after, I'm not yet sure because the weekend after is my birthday weekend. Maybe I'm doing something. So still pending about the weekend of the 24th, 25th of June. Need to figure that out. But Cup of Cosmology should be online next Saturday, 17th of June, unless I put out a tweet cancelling it. So if you don't see anything, you can assume that I'm online Saturday next week. So thank you everyone for joining today. It's been really, really good fun. Great to see everybody as always, and thank you for all of the cool questions. If you haven't done so yet, please do like, subscribe, leave a comment, share the video out, help me reach the 8,500 views by the end of today. I'm almost there, so feel free to share out the video, just push us over to 8,500. It would be nice if exactly 18 months after, it's just round numbers, we like round numbers, 18 months after starting on YouTube, 8,500 views, it's just nice. In any case, please do all the usual YouTube stuff. Thank you everyone for joining. This has been really, really fun. I hope to see you all again next week, probably on Saturday. And I hope in the meantime, you'll stay safe and take care.